Hi everyone, Dr. Burns here with our third lesson in Chapter 9, Chemical Reactions in Aqueous Solutions. In today's lesson, we're going to be covering concentrations of solutions and aqueous reactions and chemical analysis. Get your calculators out because we are going to be doing a fair amount of math in today's lesson. So we've talked about solutions in the past, and we stated that solutions were defined as homogeneous mixtures. The relative amount of a component in the solution is known as the concentration. Solutions are made up of solutes and a solvent. A solute is the substance that is dissolved in the solvent. The solvent is the medium in which the solute is dissolved in. An example of this is powdered drink mixes, which would be considered your solute, which would then be dissolved in water, which is your solvent. You could also see this as putting sugar in your coffee. Molarity, which we denote by the variable m, or also molar concentration, is defined as the number of moles of solute in exactly 1 liter of solution. So molarity is a new unit to us, and it is the concentration unit. Because it relates the amount of solute in a specific volume of our overall solution. Molarity has units of moles over liters. Molarity by itself is a unit, but it is a derived unit, meaning it is made up of units of other types. So it's made up of mole units as well as volume units. If you know the moles of your solute and the total volume of your solution, you are able to find the molarity or the concentration of that solution. We can vary our molarity by changing the amount of moles or changing the volume of our solution. I like to give the example of, think back to when you were a kid and you were drinking Kool-Aid, and you had Kool-Aid mixes that you would put into a pitcher and add water. If you put the Kool-Aid in first and then added a little bit of water, let's go with Fruit Punch Kool-Aid and it's red. You added in just a little bit of water and it was a very, very dark red color, okay? And if you tried to drink it, it would be very, very sugary. So we had a lot of our Kool-Aid mixture and not a lot of liquid. Therefore, we had a high concentration of sugar and Kool-Aid in the pitcher. If we added more water to our pitcher, the 2 gallons that it asked for on the package, okay, we add more water, that color, that red color, is no longer dark, becomes lighter, and when we go to drink it, it actually tastes good. So by adding volume, by adding more liquid, okay, by increasing that volume, we've decreased our concentration. So it's less concentrated, it's less sugary when we drink it. So that's a good example of molarity in our daily lives. So we can calculate molarity if we know the moles of our solute and the total volume of our solution. Now what I want to point out are the units that we have to use. If we want to have proper molarity for concentration, we must have moles of solute and liters of solution. So in our example here, suppose a 355 milliliter soft drink contains 0.330 moles of sugar. Calculate the molar concentration of sugar in the drink. So we want to know the concentration of our solute, sugar, in our overall solution. We have our mole value, that's 0.330 moles. Our volume is given as 355 milliliters, but we can't use that unit. I should say we can use the number, we can't use that unit because we need our units to be in liters. So before we can solve this problem for the concentration, we have to convert our volume into units of liters. So the first thing we're going to do is take 355 milliliters, and we are going to convert that to liters. In 1 liter, there is 1,000 milliliters. So to convert that, all we do is take 355 and divide it by 1,000. And we get that the volume is actually 0.355 liters. Now that we have our volume in units of liters and our moles in units of moles, they were given to us, we can now solve for molarity. So molarity, M, is equal to moles of solute, 0.330 moles, divided by the volume in liters, which we solved to be 0.355 liters. So to solve for the concentration, we just take that mole value and divide it by our volume. And we get 0.929577 moles per liter. With sig figs, this would come down to 0.930. Okay, 3 sig figs, 1, 2, 3, 1, 2, 3. So we would stop here. That 5 would round our 9 up to a 10 or to 29 to 30. And our units for this, we can express molarity either as moles per liter, or we can write this as 0.930 capital M molar. Capital M is our unit for molarity. We want to make sure we're making a difference between little m, which is meters, and big M, which is molarity. Okay, so capital M is molarity, and yes, there is a big difference. So you want to make sure you're using the capital M. I don't want to say that I took moles and liters and somehow turned them into meters. That would be very confusing how we did that. So we have capital M. But because molarity is a derived unit, you could also write it as moles per liter. Okay, so that was an example of where we knew our moles and we knew our volume, and we wanted to find our concentration. Our next example is one where we know the concentration, we just defined it as 0.930 molar, and we want to find the moles in a specific volume of that solution. So if I know molarity and I know volume, I can also solve for moles. Okay, this is just one of those equations where if we know two of the variables, we can solve for the third using algebra. So for this one, we know the molarity, that's that 0.930. We know the volume, it's saying in approximately 1 sip, which is about 10 milliliters. So we have to solve for the mole value. Now again, we have to pay attention to our units. 10 milliliters will not work out. Okay, our units will not cancel if we used milliliters. So we need to convert 10 milliliters to liters. So again, we start with 10 milliliters and we multiply this by 1 over 1,000, because in 1 liter there's 1,000 milliliters. So 10 divided by 1,000 is 0.010 liters. Just keeping that extra 0 on there for sig fig purposes. Okay, so now that I have my volume in liters, I can now plug everything in and solve for my moles. So molarity is known. It's 0.930 molar. I'm going to write that molar instead as moles per liter so we can see how our units cancel. And that equals X number of moles. We don't know those yet. That's what we're solving for. And over our volume, which is 0.010 liters. So to solve for moles, we just have to multiply both sides by 0.010 liters. Okay, so that will cancel out there. And what will happen here is my liters are going to cancel. Let me show this in a different color. My liters are going to cancel with my denominator of my units of molarity. Okay, molarity again is a derived unit made up of moles and volume in liters. So when I take a volume and multiply it by the molarity, the liter unit cancels. And I'm left with a unit of moles, which is what I want my units to be in because that's what I'm solving for. So we take 0.930 and multiply it by our volume, and we get that our moles is equal to 0.0093 moles. With sig figs, this would be 0.0093 moles. So we took our known molarity and our known volume and used that to solve for moles. We could also do the same thing if we knew moles and knew molarity, we could solve for volume. Again, this is one of those equations where if you know two of the variables, you can solve for the third. So I want to introduce you to the molarity triangle. A great way to solve molarity problems is with the molarity triangle. When you have a molarity problem, all you have to do is cover up the variable you are solving for, and the triangle will tell you what needs to be multiplied or divided together. So here's our molarity triangle. A vertical line means multiplication, and a horizontal line means division. So if I wanted to solve for molarity, all you do is cover up the M, so we're solving for capital M, and so what you would do is take moles and divide it by liters because those are the only two left in the triangle. So moles divided by liters. The other example I have for you is the one we just did. We want to find moles from molarity and volume. Well, all you do is you cover up the variable that you're solving for. So we're solving for moles. We're going to cover up moles, and that tells us we have to take molarity, multiply it by liters, right? In order to get these two, I had to go through a vertical line, which means multiplication. So I covered up moles, and I now have to take molarity and multiply it by liters. And that's exactly what we did in our previous problem when we took 0.010 liters and multiplied it by our molarity of 0.930. We got out from this equation a mole value because this unit of molarity can be rewritten as moles per liter, where when we multiply the volume and the molarity together, the liter unit cancels and we're left with units of moles. The molarity triangle helps us remember what needs to be multiplied or divided in order to solve for molarity. So let's practice using that. Distilled white vinegar is a solution of acetic acid in water. A 0.500 liter vinegar solution contains 25.2 grams of acetic acid. What is the concentration of the acetic acid solution in units of molarity? Well, we know our volume from this problem. We, however, don't know our moles, but we do know our mass, and if we know the mass of a compound, we can find the moles. So before we can plug moles in, we need to convert from mass to moles. Now, using our molarity triangle, we want to find the concentration. That's uppercase M. So to find concentration, we cover up the M, and we say that moles has to be divided by liters. So once we find the mole value, we'll just take that and divide it by our volume, which is already in liters, and we'll be able to find our molarity. Okay, so let's start. Let's first convert our mass into moles. We have to convert first, okay? We can't convert later because then that wouldn't be the correct value for molarity. So we take the mass, 25.2 grams of acetic acid, which I'm just going to show as AA, and to convert it from mass to moles, we need to use the molar mass. Molar mass has units of grams per mole. So in order to cancel out grams, I need to put the mass on the bottom and the 1 mole on the top. I can write that one better. There we go. The molar mass of acetic acid is 60.05 grams. We can find that because we have the formula for it, so we can just use our periodic table to solve for the molar mass, like we've done multiple times in our lessons so far. So we're going to take that 25.2 and we're going to divide it by 60.05. That way our grams cancel and we're left with units of moles. So that gives us a molar value of 0.41965 moles of acetic acid. Now that we have moles, we can solve for molarity. So molarity is equal to the mole value, 0.41965 moles, divided by the volume, which is 0.500. And all we have to do is divide those two numbers together. So we're going to take that mole value, divide it by 0.50, and we get a molarity of 0.839300 molar. We have 3 sig figs for our final answer, so this should be 0.839 molar for our concentration of acetic acid. Let's do some more. We have 2 problems here. We want to know how many grams of NaCl, sodium chloride, are contained in 0.25 liters of a 5.30 molar solution. Well, this one is similar to our previous example where we have volume and we have molarity, and we need to find, in this case, grams, but the only way we're going to get to grams is to first go to moles and then to grams. So we'll use our volume and our molarity to get moles out. And then we can use that to convert to grams using the molar mass of NaCl. Okay, and then the second problem says the concentration of acetic acid in white vinegar was determined to be 0.839 molar. What volume of vinegar contains 75.6 grams of acetic acid? So this is also similar to an example we did previously. So what I want you to do is pause your video and try to solve both of these problems using we have both of our equations for molarity and our molarity triangle here. So use both of those to help you solve these problems. Both the molarity equation as well as the molarity triangle are provided to you in your resources when taking exams. So getting used to using them now will help you when you go to do your homework and when you go to do your exams. So pause your video and practice these 2 problems. For our first example, using the molarity triangle, if we want to find moles first, before we can go to grams, we're going to cover up moles, and we say that the molarity needs to be multiplied by the volume. So that's our first step. We're going to take 0.250 liters and multiply it by 5.30 molar. Again, we can rewrite molar as moles per liter. So we can see that our liters are going to cancel, and we're left with, let's see, 0.250 divided by 5.30. So we get, oops, not divided by, my bad, 0.250 times 5.30. There we go. And that will be a mole value of 1.325 moles. That's moles of NaCl, but I want to find grams. So to find grams, we're going to have to use the molar mass. If I want to find grams, grams will go on top, 1 mole will go on the bottom, and the molar mass of NaCl is 58.44. Again, we can use our periodic table to find that molar mass. So we'll take that mole value and we'll multiply it by 58.44, and we get 77.433 grams. With sig figs, that'll reduce to 77.4 grams of NaCl. Okay, our second problem, we have to, let's see, we're solving for volume. So we're going to cover up our volume unit now, and we say that we need to take the mole value and divide it by the molarity. Remember, a horizontal line means division. So we'll take moles and divide it by molarity to solve for the volume. So what we need to do first is find our mole value. We have our concentration, we solved for that in our previous examples, but we have a mass again. So we're going to do what we did before and take that mass of acetic acid and convert it to moles using its molar mass. So we have 75.6 grams of acetic acid, and we're going to divide it by its molar mass of 60.05 grams per 1 mole. So 75.66 divided by 60.05, and we get that our mole value is 1.25995 moles of acetic acid. So to find the volume now, we're going to take our moles and divide it by our molarity. So we'll take 1.25995 moles, divide it by the molarity we solved for, 0.839 molar. Again, we can rewrite molar as moles per liter. Moles will end up canceling when we do the division, and we'll be left with units of liters, which is what we want if we want to have a volume at the end. So we'll take that 1.2599 and divide it by 0.839. And we get a volume of 1.5017 liters. So when we divide moles by molarity, our volume unit is already decided for us, and it is going to be liters. If the problem asked for the volume in milliliters, then you may have to do an additional conversion to go from liters to milliliters, because molarity units are specifically moles per liter. Okay, so with sig figs, this would be 1.50 liters, 1.5 liters. Okay, let's do a few more. I want you to try these independently. I also don't have the molarity triangle on here, but you should have it in your notes. It's in your note pack. So utilize each of these to calculate the molarity of each of the solutions below. I'll give you a little hint here. I'll give you the molar masses for the 3 compounds, so you don't have to spend your time calculating those. So methanol is 32.04 grams per mole. Calcium chloride is 110.98 grams per mole. and naphthalene is 128.17 grams per mole. So those are their molar masses, so you can convert grams to moles and then use that to calculate your molarity. Remember, we have to convert milliliters to liters, and that in 1 liter, there's 1,000 milliliters. So use these conversions and pause your video and solve these 3 problems. The first step for each of these problems is to convert all of our units or all of our values into the proper units. So the first thing that we're going to want to do is take our masses, 6.57 grams, and divide them by their molar masses. We'll do one at a time. So 6.57 divided by 32.04. So we get a mole value of 0.20506 moles. We also need to convert all of our volumes into liters. So we have 1.50 times 10 to the 2 milliliters. There's 1,000 milliliters in 1 liter. So we'll take 1.5 times 10 to the 2. Oops, that's not a 2. That's a 2. And we'll divide it by 1,000. So we get 1.5. No, 0.15, sorry. Liters. Okay, and then to solve for molarity, we then just take those two values, 0.20506 divided by our volume, we get our molarity out, 1.36. That's what, 3 sig figs? There we go. So that should be 7 with rounding. Molar. 1.37 molar for our first one. For our second one, we're going to do the same thing. We're going to start with 10.4 grams. And we're going to divide by the molar mass of 110.98. So we get a mole value of 0.093710 moles. And for our volume, we'll just divide that by 1,000 again. Which is 0.22. Okay, so then for molarity, we take those two values, 0.093710 moles, and divide it by our volume, 0.22 liters. 3710 divide by 0.22 to get a molarity of 0.426 with 3 sig figs. Okay, and our last one, the same steps. 7.82 grams divided by the molar mass of naphthalene, 128.17. What is happening? 7.82 divided by 128.17. 061013. Okay, and our volume we just take and divide by 1,000. Let me get that volume in liters. So we just take those two values and plug them in to find the concentration. So we take 0.061013, divide that by 0.0852. And we get 0.716 molar. Okay, so for these ones, all we did was convert from grams to moles, and then we converted milliliters to liters so that both of our values were in units of moles and in liters. Then once we had those values, we just divided them to find the molarity. For our next set of problems, we want to calculate the volume needed to make the following solutions. So I give you the concentrations as well as the masses, and now we want to find the volume. So again, I will give you the molar masses for each of these. NaCl is 58.44 grams per mole. And our second one, acetic acid, we did before, is 60.052 grams per mole. I did not specify what volume unit I wanted, so let's just go to liters and we can avoid the conversion. So let's get a volume in liters. So pause your video and try these two problems. For these problems, we're going to take a similar approach where we're going to start by converting our masses to moles using our molar masses. So we'll take 2.14 grams and divide it by its molar mass. So 2.14 divided by 58.44. Okay, once we have our mole value, then we just need to take our concentration and do moles divided by molarity, and that'll give us our volume. So if we use our molar triangle, we cover up the L, the liters, and we see that moles need to be divided by the concentration in order to solve for liters. So we will take our mole value, 0.036618, divided by the concentration given in the problem. Okay, and by dividing those, we get volume out. So we get 0.1353 liters. With sig figs, this would be 0.136 liters. If the problem asked you to convert to milliliters, then you would take it from there and convert it from liters to milliliters using our conversion. But I said let's stop at liters to avoid that. But just keep an eye on the problem on your homework and your exams on what unit they're asking for, because you may need to do some additional conversions. Okay, so the next problem we'll solve in a similar way. We'll take that mass, 0.85 grams, divide it by the molar mass, 60.052. And we get 0.01415 moles out. Now that we have moles, we can take our concentration and do our moles. 0.01415 moles divided by our concentration of 0.30 molar. So doing that, we get a volume of 0.04718, and that has units of liters. Again, just to show how our units are canceling, we have molarity, which is moles per liter. We have moles on top and bottom, so when we do the division, the liters will be left over. Okay. So with sig figs, this would be 0.047 liters because there's 2 sig figs in our concentration. Okay, we can use concentrations and pair that up with something called a dilution. So dilution is the process whereby the concentration of a solution is lessened by the addition of solvent. As the volume increases, our concentration will then decrease. Dilution is used to prepare solutions of a desired concentration. By adding solvent to a measured portion of a concentrated stock solution, a solution of a lesser concentration may be prepared. So we're always going to start with a concentration that's high and a volume that's low. And those are in comparison to our end point, which will have a lower concentration and a higher volume. Okay. We have a mathematical relationship that can be used to describe our dilutions, okay? And we relate the volumes and the concentrations of the solution before and after the dilution process. And that relationship is these variables here, this equation here. M1 V1 equals M2 V2. So M stands for molarity and V stands for volume. 1 is initial and 2 is final. So another expression, another version of this expression is MI VI equals MF VF. Molarity initial times the volume initial is equal to the molarity final times the final volume. So you can use either one of these to do a dilution. And the idea here is that M1 will always be larger than M2, and V1 will always be smaller than V2, because the process of the dilution increases the volume, which in turn decreases the concentration. When doing a dilution, we can never go from a high concentration to an even higher concentration. That'll never happen because M and V are inversely related. As one goes up, the other goes down. Okay? So we'll always have this relationship here. M1 is larger than M2, and V1 is always smaller than V2. So let's practice with this, because the best way to learn these types of problems is through practice. So if a 0.850 liters of a 5.0 molar solution of copper nitrate is diluted to a final volume of 1.8 liters by the addition of water, what is the molarity of the diluted solution? So these problems, with dilution problems, we get a lot of numbers, and we just need to figure out what volumes go with which concentrations and what we're solving for. Okay, so we always want to make sure we're defining the correct values. So M1, V1, M2, V2. We're going to define each of these based off of the wording of the problem. So we're saying that this solution of copper nitrate is diluted. So the pre-diluted solution is going to be our initial solution. So we're going to look at these values here for our M1 and our V1. So we have 0.850 liters of a 5.0 molar solution. So our initial molarity is 5.00, and our initial volume is 0.850. Okay, so usually we see them paired up using like of A or within A. Okay, the wording of the problem will tell you what volume goes with what concentration. For our M2 and our V2, well, the problem then states we have a final volume of 1.8 liters and we want to find the molarity. So molarity 2 is unknown and volume 2 is 1.80 liters. So for this problem, we just plug it into our M1 V1 equals M2 V2. This is an equation where we know 3 of the 4 variables, so we can solve for the 4th. So M1 is 5.0 molar, and V1 is 0.850 liters. And that is equal to some value of M2, which we're solving for, multiplied by V2, which is 1.80 liters. Okay, so now we just have to do a little bit of algebra. We're going to move that 1.80 liters to the other side by just division. Okay, that'll allow us to cancel out the liter units and be left with molar units, which is what we want because we're solving for M2. So we take 5.0, we multiply that by 0.850, and we then divide by 1.8. So we get that M2 is equal to 2.36 molar. We can check V1 is smaller than V2, and M2 is smaller than M1. Now I'd like to make a note here about our units. So the volume units and the molarity units, they don't technically matter as long as our 1 and our 2 are of the same unit. So because our volumes here were in liters, they're both in liters, then those units would cancel. If for some reason one of these was written in milliliters, let's say this first one was written as 850 milliliters instead, then we could not use this number directly with this one because they're not of the same unit. So you have to make sure that your volume units are the same. Now, if the problem gives you 2 values of volume in milliliters, you don't need to convert it. So if we're given V1 and V2 in milliliters, we do not convert. because if we were given two volumes, we would be solving for a molarity. So if, let's take the case of this problem, we have M1 is what we're given. If we had V1 in milliliters and we divided by V2 in milliliters, those units would still cancel and I would still be left with units of molarity. Okay, so if the volume units are the same, regardless of what that unit is, milliliters, liters, kiloliters, as long as they are the same, then you can use them as is and you can solve your problem based off of that. If you start with a volume in milliliters and you're asked to find another volume, you could also choose not to convert that to milliliters. You would just have to remember that the volume you get out is in units of milliliters. Okay, so if we're solving for volume, we would have M1, B1, we would be dividing by M2. Okay, let's say our V1 is in milliliters. Well, our two molarity units would cancel. My volume of V2 would be in units of milliliters because my value of V1 was in units of milliliters. So you just have to keep an eye out for that. If the problem asked for the second volume in milliliters, then you're fine. But if it asked for it in liters, you'd have to convert. Okay, so just keep an eye out on your units and remember that if we're comparing two of the same thing, like two volumes together, as long as they are the same unit, they can be compared. And if you're solving for a volume and you're given a volume in milliliters, you can either convert it or you can leave it as is and remember that your final volume will be in that same unit. Okay, let's keep practicing. So what volume of 0.12 molar HBr can be prepared from 11 milliliters of 0.45 molar HBr? So here's a good example of what we were just talking about our volume. So our equation, let's put it up here, is M1V1 equals M2V2. For this problem, I'm going to put it right up here for space purposes. I have my M1 is defined as 0.45 molar because it's larger than my second molarity, so we automatically know what M1 and M2 are. So 0.45 molar and 0.12 molar. And because the problem says I have 11 milliliters of that 0.45 molar solution, that means that's our V1. So we have 11 milliliters. I can leave the milliliters as is. I don't specify what volume unit I want in here. Your ALEKS homework will. Okay, so let's say that I want this unit to be in liters. Let's just say that, okay? So we can keep that milliliters as is and we can do our math accordingly. So this would be, if I'm solving for V2, I would have M1 times V1 divided by M2, right? I'm just solving my equation up there to solve for V2, just using basic algebra. So I'm going to take 0.45, multiply that by 11, and I'm going to divide that by 0.12. So my V2 is now 41.25 milliliters. Okay, so V2 is higher than V1, which is what a dilution is by adding more volume. Now, my volume unit is milliliters because the unit here is milliliters. My molarity value canceled, okay, so I'm left with units of milliliters. The problem, I say, I want it in liters, so we would have to take that 41.25 milliliters and we would have to divide it by 1,000 in order to get it to liters. So that would be 0.041 liters with sig figs. Okay, so that's what I mean by just keeping track of your units. You don't have to convert unless the problem specifies. For these last two problems, I want you to try both of them independently. So pause your video. I'll get your M1, V1 back up there. There we go. Pause your video and try these last two problems on your own. For our second problem, we can define our M1 and our V1 and our M2 and our V2. We say what volume of a 1.59 molar KOH solution is required to prepare a 5 liters of a 0.1 molar KOH. So we have a higher concentration and a lower concentration, so that automatically defines our M1 and our V1. M1 is going to be the higher one, and M2 is going to be the lower one. And we're given 5.0 liters of that 0.1 molar solution, so that's going to be our V2. Okay, so we're then going to take that. Let's see, we're solving for V1, so I'm going to do M2 V2 over M1. So we get 0.100 times 5.00 divided by 1.59. And we get out 0.100 times 5. Divide that by 1.59. We get 0.314 liters, right? This value for volume is in liters. Molarity will cancel between M1 and M2. And if we were asked for milliliters, we would then just multiply by 1,000. To get 314. Again, I did not specify, so just check on your ALEKS homework and on your tests to what specific units they want. They will tell you. Okay, for our last problem, we're solving for a concentration. So what is the concentration of the solution that results from diluting 25 milliliters of a 2.04 molar solution of methanol to 500 milliliters? So we have M1, V1, M2, V2. So M1, we'll look at V since we're solving for concentration. So we have 25 milliliters and 500 milliliters. V2 is always going to be higher than V1. And since this is 25 milliliters of a 2.04 molar solution, 2.04 is our M1 concentration. So we solve for this one. We're going to take M1 V1 and divide by V2. So we'll take 2.04 molar times 25.0 milliliters, divide by 500 milliliters. We don't need to convert our volume units because they end up canceling anyways, and we're left with molarity units. So this is another example where we don't need to convert. Okay, so we get 2.04 times 25 divided by 500. And we get 0.102 molar for our solution, which is less than our initial concentration, which is as expected for a dilution where we are decreasing our concentration. So that's a great way to always check your work, that your volume, your V2, should always be larger than V1, and M2 should always be smaller than M1. Let's do a few more. What volume of 2.0 molar HCl solution is needed to dilute to prepare 1 liter of a 0.646 molar HCl solution? So we have M1, that's going to be 2.0 molar multiplied by V1, which we're solving for. And then we have M2 and V2, 0.4646 times 1. So we'll take 0.646, multiply it by 1, divide that by 2 to solve for V1. So V1 is we need 0.323 liters of our initial solution to dilute to 1 liter and get a desired concentration of 0.646. And for our last example here, I want you to try this one independently. Water is added to 75.0 milliliters of a 0.992 molar KNO3 solution until the volume of the solution is exactly 250 milliliters. What is the concentration of the final solution? So try this one on your own. We're looking for M2. We know V1 and M1, so we have 0.992 molar for M1 and 75.0 milliliters for V1. We want to find M2 and we're given V2. Again, we don't need to convert our volume units because they are both in the same unit, so they will end up canceling. So we're going to take 0.992, multiply that by 75, and divide that by 250. So we get M2 as being 0.298 molar with 3 significant figures. Okay, so how are we going to use concentration? Well, with acids and bases, we can use that to quantify how acidic or how basic something is based off of its concentration. And we call this the pH scale. So the acidity of an aqueous solution depends on the concentration of hydronium ions. And remember, the hydronium ions result from hydrogen ions coming together with a water molecule, creating H3O+. And we learned about that when we talked about acid and base reactions. The pH of a solution is defined as the negative base 10 logarithm of the hydronium ion concentration, as long as that concentration is in units of moles per liter, which we know as molarity. We show concentration in square brackets. So that little square bracket that's around the H3O+, that stands for concentration. So we can define pH as the negative log of the H3O+ concentration. We can also take a pH and solve for the H3O+ concentration by doing the opposite of a base 10 log, which is 10 raised to the negative pH. So in pure water, the H3O+ concentration is 1.0 times 10 to the minus 7 molar. Therefore, we can plug this concentration right in to H3O+ and put that into our calculator to solve for the pH of 7. So what I want you to do is pull out your calculator, because logs are not something that everyone remembers how to do on a calculator, especially if it's a new calculator to you. Okay, you can also try this on your ALEKS as well. Make sure you know how to use this. Okay, if your standalone calculator does not have a log button or a 10 raised to the button, then you'll have to use the ALEKS calculator to do these problems on your homework and the exams. So, to solve for pH, we want to do our pH is equal to the negative log of our concentration, and for water that's 1.0 times 10 to the minus 7 molar. So to type this into our calculator, we would do the negative button, and then we would do the log button, and then we would type in our concentration. Let me get our answer. If you have a calculator that is not one of the graphing calculators, and if it's a smaller one, some of them require you to type in the concentration, like type in the number and then hit the log button. Okay, so please try this on your own calculator so that you know how your calculator works specifically, so that you're not lost on your homework or your exams. Okay, so, and again, you can also try this on the ALEKS calculator. You will always have the ALEKS calculator on your screen, so you can always use that. But on graphing calculators, that's how you plug this in. If it's not a graphing calculator, if it's one of the small calculators, you usually have to type in the concentration and then hit the log button and then remember to change the sign. So keep that in mind. Please practice it on your own calculator. If you do not know how to do it on your calculator, if you're looking at it like, how do I do this? You can either, one, send me an email and show me what calculator you have, and I will tell you how to do it because I've seen it on all calculators. Or go to good old YouTube, search the type of calculator you have, and type in how to do a log function, and I guarantee someone has a YouTube video about it. So please know how to use this on your own calculator. Okay, so for pH, we just type in our -10 to our concentration. If we wanted to know the concentration from the pH, so let's say we knew the pH of water was 7, we would plug that in. So to do that, again, on graphing calculators, you want to do second log button. That gives you a 10 raised to the. This 10 raised to the is different than our scientific notation 10 raised to the. So just keep that in mind. It is different. Okay. I don't want to get into all the differences with base 10s and everything like that on calculators. It's a whole thing. So just hit second log and that'll give you 10 to the. Then you do negative of your pH. So whatever the pH value is, you just do the negative of that value, and what comes out is your concentration. So we know our concentration at pH of 7 is 1 times 10 to the minus 7 molar. Okay, so we'll practice that. The pH scale is logarithmic, so it's base 10. Okay, so everything is different by a factor of 10. So here on our pH scale, we see what's in red is more acidic, so it has a pH of a really low number. So low pH is acidic. And then we go down to the higher end in the blue. High pH is referred to as basic. So low pH things, acidic things, these are going to be like foods that we eat every day and drinks and everything, because our stomach is acidic. So we ingest more acid-based foods so that it works with our body. And more basic things are going to be like cleaning supplies and other things that, if ingested, could kill you. That's just how I remember it. Things that we ingest should be like our bodies, which is acidic. So basic things, if we ingest them, such as cleaning supplies, they would kill you. So, okay. And you can see that our concentrations relate to our pHs. So something I like to point out is that if you look at the exponent on these concentrations, the positive version of that exponent is your pH. So a good way to check your work is if you know the concentration and you're trying to find the pH, well, look at your exponent. It should be around that number. Okay, so it's a good way to check your work. So yeah, that's our pH scale. It ranges from 1 to 14, and it ranges by that because of the logarithmic scale. So let's practice that. Let's practice putting these in. Please use your own calculator like the one you're going to be using on your exams. Don't use your phone's calculator because you're not using that on your exams. Use the calculator that you are going to be using. If you want to pull up your ALEKS homework right now, just to have the calculator present, go for it and type it in with me. So for these, we want to determine the pH of each solution with the following hydronium ion concentrations. So for these ones, we're going to use this equation. So our pH is going to be equal to the negative log of the concentration given. And again, our little trick, our number for pH should be around 4. So that's what we're looking for, approximately 4 for our pH. So let's plug that into our calculators. On mine, I do a negative log, and then I type in my concentration, 5.3 times 10 to the minus 4. And I get a pH of 3.3 with sig figs, which is near 4. It's within 1 pH unit of 4. So there we go, checking our work. Okay, for your next two, I want you to try those on your own. Please type them into your own calculator so that you know how to use it and you're not at a loss when you go to do your exam. So try these on your own calculator now. The setup for these is the same. pH is just equal to the negative log of that concentration. Again, we should be around 6 and around 12 for each of these, give or take 1. Okay, so we do negative log of 7.1 times 10 to the negative 6. 5.1 for our pH. And then we have negative log of 4.8 times 10 to the minus 12. And that is 11. And I don't think I said this explicitly on our previous slide. It was written, but I don't think I said it in words. So I'll write it up here. pH is dimensionless, which means it is unitless. So it does not have a unit. So these are all unitless. We don't put a unit at the end of them. Okay, so we've solved for the pH from some concentrations. Now let's do the opposite, and let's use this equation where we're given the pH and we want to find the hydronium ion concentration. So we have some pHs here. We want to plug these into our calculator. So I'll do the first one and then you'll solve the rest on your own. So if we want the hydronium ion concentration, what we're going to do is take 10 and raise it to the negative pH. So here it's 5.20. So in my calculator, I do second log, because there's a 10 raised to the, and then I do negative 5.2. Okay, and again, this pH is now going to tell me approximately where my exponent should be in my concentration. So it's going to be around 5. So we have 6.31 times 10 to the minus 6, which is close to 5. Okay. So for these next ones, I want you to try these on your own. Again, typing this into your own calculator that you are going to be using on the homework and the exams so that you are comfortable and prepared to do that independently. So again, this just becomes 10 raised to the negative 16, 10 raised to the negative 11.20, and 10 raised to the negative 2.42. So second log negative 16, we get 1.0 times 10 to the negative 16. I think this should have 2 extra zeros on there for sig figs. Second log negative 11.20. Oops, I did the wrong one, sorry. Second log, there we go. That was an incorrect number. Negative 11.20, there we go. So we get 6.30, let's do 10 for rounding, times 10 to the minus 12. So it should be around 11, 12 is close to 11. So then our last one, log, we do negative 2.42. So we get 0.00380 molar. These should all have units of molarity because we're solving for the concentration. Remember, square brackets mean concentration. We're determining the hydronium ion concentration, so these are all concentrations. Yes, we can get units from this dimensionless quantity because that's how pH works. So we can get these in molarity. Now, we can use molarity with our balanced chemical reactions. So ionic compounds that are soluble in water are considered strong electrolytes. We learned that a few lessons ago. And we know that if they're strong electrolytes, they fully dissociate into their individual ions when they are dissolved in water. So if we look at KMNO4, when it dissolves in solution, it breaks apart into potassium ions and permanganate ions. So if we were to look in our little beaker, we have water. Okay, there's water. Let's omit the fact that some of the water's coming out. We would see K pluses floating around and MnO4s floating around. Okay, so they would be floating around. In this example, 1 mole of potassium permanganate separates into 1 mole of potassium ions and 1 mole of permanganate ions when they're dissolved in water. We know that because of our balanced chemical equation. Those coefficients out in front of each of our compounds are 1. If we know the concentration of potassium permanganate solution, we can then use our mole-to-mole ratio concept to determine the concentration of each individual ion in solution. So, assume we have a 0.50 molar solution of potassium permanganate. Let's determine the concentration of both ions in solution. So here's where remembering that molarity is units of moles per liter comes in. Because if we know moles of something, we can convert to moles of something else. So we're going to start with 0.500 moles per liter of KMNO4. And we first want to find our concentration of potassium. The mole-to-mole ratio between potassium permanganate and potassium ion is 1:1. Because the potassium permanganate is dissolved in solution, the volume is constant. We're not changing the volume when we add the ionic compound, and when we dissolve the potassium permanganate in solution, so the volume is constant. So our liters here is unchanging. Since liters is staying the same, we can use the moles here to convert between moles and moles of any reactant or product. So I'm going to use my mole to mole ratio. I'm going to say for every 1 mole of KMnO4, we get out 1 mole of potassium, meaning the potassium ion concentration is 0.500 moles per liter. The only unit that I canceled when I did this conversion was moles of KMnO4. I'm left with moles of K plus and liters, which is still a concentration unit. So since volume is unchanging, it just stays there. It does not cancel out. We can do the same thing and solve for the permanganate ion. So we again start with 0.500 moles of KMnO4 per liter. And now we can convert between 1 mole of KMnO4 is 1 mole of MnO4 minus. Again, the only unit I'm canceling is moles of KMnO4. So my permanganate ion concentration is 0.500 moles per liter of MnO4 minus. So we can use our mole to mole ratio and our molarity, and the fact that molarity is a derived unit from moles, to convert. So let's try a few more. We want to determine the chloride ion concentration in a 1.02 molar solution of silver chloride. So the first thing we want to do is show how silver chloride breaks up into its ions. We want to take its charges into account. So we have AgCl3, which breaks apart into Ag3 plus and Cl minus. But in order to balance this, I have 1 silver, 3 chlorides, 1 chloride. So I need to add a 3 in front of my chloride to properly balance it. So when I put silver chloride into solution, AgCl3, when it breaks apart into its ions, let me draw our thing again. Get some water in there. So there's my beaker. For every silver ion, I have 3 chloride ions. So there's more chloride ions in solution in comparison to silver ions. So we now want to determine the chloride ion concentration in that 1.02 molar solution of silver chloride. So we're going to set it up the same way. We're going to start with 1.02 moles per liter of silver chloride. And we're going to use our mole to mole ratio to find the concentration of just the chloride ions. So for every 1 mole of silver chloride, we get out 3 moles of chloride ions. So we're going to take 1.02 and multiply it by 3. So our concentration of the individual chloride ions is 3.06 molar. The concentration of the individual chloride ions is 3 times higher than the solution overall, because there are more chloride ions for every silver ion. So I have 3 times more in solution. For our second one, we want to determine the chloride ion concentration in a solution of barium chloride. So we're going to start this out the same way. BaCl2 is going to break apart into barium 2 plus and Cl minus. But again, to balance, I need to put a 2 out in front of that chloride to balance it out with that 2. So we start with our initial concentration, 0.150 moles per 1 liter of barium chloride. Remembering that our volume is unchanging, and that's how we're going to continue to have the same volume. Okay. Now we're just going to convert from 1 mole of barium chloride creates 2 moles of chloride ion. So we take 0.150 and we multiply it by 2. And we get 0.300 molar concentration for Cl minus. The concentration of individual chloride ions is twice as high as the overall solution because when it breaks apart, I get 1 barium and 2 chlorides. So if I were to look at the entire solution, I have a lot more chloride atoms in comparison to barium atoms. And since concentration is the one part that you're looking at over the whole, the entire solution, if there's more of one type of atom, it's going to have a higher concentration. So let's do some more. We want to determine the sodium ion concentration for each of the following solutions: sodium sulfate, sodium carbonate, and sodium bicarbonate. So the first thing you're going to want to do for these problems is independently write out what the chemical equation looks like when this molecule breaks apart into solution. So try that on your own right now. Sodium sulfate, Na2SO4, breaks apart into 2 sodium and 1 sulfate. Sodium carbonate is similar. Na2CO3 breaks apart into 2 sodium and 1 carbonate. And sodium bicarbonate, NaHCO3, breaks apart into Na plus and HCO3 minus. Okay, so now that we know what this breaks into, we can use our mole-to-mole ratios to solve. So we have 3.25 moles per liter of sodium sulfate. So we use our mole-to-mole ratio. For every 1 mole of sodium sulfate, I break apart into 2 moles of sodium. So we take that 3.25 and we multiply it by 2. It's 6.50 moles of Na plus. Oop, not moles, moles per liter. There we go, concentration units. Next up, we have 1.78 moles per liter of sodium carbonate. And again, we use a 2-to-1 mole ratio because for every 1 mole of sodium carbonate, I break apart into 2 moles of sodium. So 1.78 times 2 is 3.56 molar concentration of sodium ions. And finally, we have sodium bicarbonate. This is now in a 1-to-1 ratio, so for every 1 mole of sodium carbonate that I put into solution, I break apart into 1 mole of sodium ions. So my sodium ion concentration is 0.585 moles per liter, molar. Okay. These ones are getting a little bit harder. Now we want to know what is the concentration of strontium nitrate solution that has a nitrate ion concentration of 2.55 molar. So we know that the concentration of NO3 minus is equal to 2.55. So we want to go back and find the original concentration of the solution overall. So we're going to start this problem in the same way. We're going to take strontium nitrate, and it breaks apart into a strontium 2 plus and 2 nitrates. Okay, that 2 is coming from our balancing. So if I know my initial concentration of nitrate is 2.55 moles, again, our volume is unchanging. This is of NO3 minus. We now can use our mole-to-mole ratio and put moles of nitrate ion on the bottom because we want it to cancel out. And we put moles of strontium nitrate on the top so that we're left with that value. We can now put our coefficients out in front. Nitrate has a 2. Strontium nitrate has a 1. So we're going to take 2.55 and divide it by 2. And we get a concentration of the overall solution to be 1.28 molar for strontium nitrate. 3 sig figs there. Now I want you to try this last one. It's similar to what we just did with strontium nitrate, but now it's lithium carbonate. And we want to know if the lithium ion concentration is 0.595, what is the concentration of lithium carbonate solution? So try this one independently. We want to write our balanced equation. So lithium carbonate is Li2CO3. That breaks apart into 2 lithium ions and a carbonate ion. So if we know that lithium ion is 0.595 moles per liter of lithium ion, we have a mole-to-mole ratio. Moles of lithium ion are going to go on the bottom so they cancel, and moles of lithium carbonate will go on top because that's what we want. We want to know the concentration of lithium carbonate. Liters is staying constant, it's unchanging, so when I have moles per liter, it'll still be a concentration. So for every 2 moles of lithium that are in solution, that came from 1 mole of lithium carbonate. So we take 0.595 and divide it by 2 to get 0.298 molar lithium carbonate. Okay, our last practice problem on this is a challenge problem. So what volume of a 0.15 molar ammonium sulfate solution contains 5.75 grams of ammonium ion? So this problem brings together multiple things that we've learned so far in this lesson. First is concentration of a water-soluble compound in comparison to its ion, which is what we've just been focusing on, but also how to find a volume from a concentration and a mass. So the first thing we're going to want to do is find the ammonium ion concentration. because that's what we're looking for. If we know the concentration of ammonium ion in the solution, and we know the mass of it, we can find the volume using our molarity triangle. Okay, so the first thing we have to do is find the concentration of NH4 from ammonium sulfate. The second thing we're going to want to do is find our moles of NH4. Okay, because the only way we can use a molarity and in order to find a volume is if we have moles. So let's first do what we were just doing on these problems. We take ammonium sulfate, NH4, 2SO4, and it's going to break apart into solution to be NH4 plus and SO4 2 minus, and there should be a 2 in front of our ammonium. So we then take our concentration of ammonium sulfate, and we use our mole to mole ratio to find the concentration of the ammonium ions. So that it's for every 1 mole of ammonium sulfate, we get out 2 moles of NH4 plus. So we take 0.112 and we multiply it by a value of 2. You get 0.224 molar NH4 plus. Now if I want to find a volume using our molarity triangle, let's see, here's my molarity triangle. I have moles, liter, and molarity. If I want to find a volume, I need to take my mole value and divide it by my molarity. So liters will be moles over molarity. I know my molarity, it's right here. I need to find my moles. So to do that, I'm going to take the 5.75 grams of ammonium NH4 plus, and I'm going to convert that to moles in the same way we did our previous problems when we did molarity. So the molar mass of NH4 is 18.04 grams for every 1 mole. So we take 5.75 and divide it by 18.04 to get our mole value of 0.31873. So I now have my mole value and my concentration. I can now plug this in to solve for liters. My moles is 0.31873 moles divided by my specific ammonium ion concentration of 0.224 molar. So we'll take that divided by 0.224, and we get a volume out in liters of 1.42 liters of NH4. Okay. So, a little roundabout way, using what we've learned previously. If you needed to use your molar roadmap, you could also do that as well. Since we're using a mole to mole ratio, it just uses molarity slightly differently than our molar roadmap does. But I did want to remind you that our molar roadmap is now complete. So I said before that we were going to ignore these two. We no longer have to, okay, because we now know what molarity is. So our molar roadmap is complete. We know how to go from moles to volume using molarity and volume to moles using molarity. So we can now use our full molar roadmap. Moving on. Moving on. We can now start to bring together many of the things that we have learned about chemical reactions, precipitation reactions, acid-base neutralization reactions, as well as solution stoichiometry. We can use different types of chemical analysis to determine how much product will form given a starting concentration of reactant, or how much of a particular substance is present in a sample. And to do this, we will use two types of chemical analysis techniques. First, we'll cover gravimetric analysis, and then we'll cover acid-base titrations. Gravimetric analysis is an analytical technique based on the measurement of mass. Gravimetric analysis is very accurate. It is a very accurate technique that chemists can use to find the mass of a certain reactant or product or piece of a compound in a given sample. Therefore, it is only applicable to reactions that go to completion or have nearly 100% yield. So let's look at an example of this. Remember, we're finding mass. So, given the following precipitation reaction, okay, we have a precipitation reaction. We're going from two aqueous solutions to a solid. We formed a solid magically, chemical magic. Answer the question below. Assume 215 milliliters of a 0.425 molar potassium phosphate solution is reacted with excess zinc chloride. Calculate the mass in grams of the solid precipitate that is formed. Well, the solid precipitate that's formed is zinc phosphate. Okay, so we want to find the mass of zinc phosphate. But all we're given is a volume and a concentration of one of our starting products. So, assuming that this reaction goes to completion and I have enough zinc chloride to get me through, I want to somehow go from concentration of K3PO4 to mass of zinc phosphate. So, what I want to do is just quickly go back to our molar roadmap up here. Okay, and zoom in a little bit. So, I'll we're starting at a volume of a solution A, and we want to get to a mass of compound B. Okay, so our starting on our previous example was K3PO4, and we wanted to get to ZN3PO42. So to do this, we're going to take the volume of our solution and we're going to use our molarity to calculate moles of K3PO4. Once we have moles of K3PO4, we can now convert to our other chemical species using a mole-to-mole ratio, also known as our stoichiometric factor. So that will get us to moles of zinc phosphate. Remember, if we're going from one chemical species to another, the only way we can do that is through a mole-to-mole ratio. There is no other way to convert from one molar species to another, only through a balanced chemical reaction and a mole-to-mole ratio. So we'll use our mole-to-mole ratio to get moles of B, moles of zinc phosphate, and if I know my moles of my compound, and I know my compound's formula, I can find its molar mass and use that to find the mass of zinc phosphate. So here's how we're using our molar roadmap now that everything is complete. We're starting with a volume, we're going to convert to moles, we'll use our mole-to-mole ratio to get to moles of our other substance, and then use our molar mass to get to the mass of our precipitate that is formed. So let's go back and solve this problem. Okay, so we said liters of K3PO4. We'll then go to moles, which will then convert us to moles of zinc phosphate. Oops. That 4 should be down there. There we go. And once we have moles of zinc phosphate, we can get to mass. Okay, so to do our first step, we need the molarity. Our second step, that's the heart of the problem, that's our mole-to-mole ratio. And then our mass, to go from moles to mass, we're going to use our molar mass. Lots of M's going on here, so we need to make sure we know what all the different M's mean. Okay, so the first thing we need to do is take our volume of K3PO4 and use our molarity to go to moles. So we have our molarity triangle. I want to find moles, so I need to take my molarity and multiply it by my volume. My volume currently is in milliliters, so I'm going to have to convert that first. So we'll take 215.00 milliliters, and we'll divide by 1,000 because there are 1,000 milliliters in 1 liter. And we get 0.1215. Okay, so now that we have liters, we're going to multiply that by our molarity. And I'll show that instead of molarity, I'll put it in moles per liter to remind us that liters are going to cancel. So we'll take that 0.215 and we'll multiply it by 0.425 to get out a mole value of 0.091375 moles. Okay, so now we're here. We now want to go from moles to moles, so we need a mole to mole ratio. So I'm taking that 0.091375 moles of K3PO4, and I'm going to use my mole to mole ratio. For every 2 moles of K3PO4, okay, I start with 2, I get out 1 mole of zinc phosphate. So I'm going to take my mole value and divide it by 2, which gets me 0.045675 moles of zinc phosphate. Okay, so that gets me to moles of zinc phosphate. Since I want to find the mass of zinc phosphate, we now have to use the molar mass to convert from moles to mass, which we've done for many chapters now. So that should be the easy part. So we're going to take that 0.045675 moles, and we are going to multiply it by its molar mass, which we can find from the periodic table, which is 386.11 grams for every 1 mole. So we'll take 0.045, multiply it by 386.11, and we get a mass of 17.6 grams of zinc phosphate. So I used my molar roadmap to tell me I needed to start with my volume, use my molarity to convert to moles. We've learned that. That was the start of this lesson, using concentration. Then we're going to use what we learned in chapter 8 to go from moles of one substance to moles of the other. And then we'll use what we learned from many chapters that we've gone through so far to go from moles to mass. So this problem, the second half of it, is some things that we've done before in previous chapters. We're now expanding on it by adding the concept of molarity being able to tell us the number of moles. Because if we know moles and we have a balanced reaction, we can convert to anything, any reactant and any product. Once we know moles of something else, we can go to molarity, we can go to mass, we can go to particles, we can go to many different things. So we're using that molar roadmap to our advantage. That molar roadmap is given to you on all of your ALEKS exams, so please use it. Let's do another one. Gallium chloride is formed by the reaction of 2.6 liters of a 1.44 molar solution of HCl according to the following equation. Calculate the mass of gallium chloride formed. Well, this problem is very similar in setup to our last one. We start with a volume, liters of HCl, and we want to get to mass of GaCl3. So, if we're converting between two chemical species, we know we need to somehow get from moles of one to moles of the other. right? That's the heart of the problem through a mole to mole ratio. So in order to get from liters to moles of HCl, we're going to use our molarity, just like we did in the last problem. And once we have moles of gallium chloride, we're going to convert that to mass using our molar mass, which we've been doing for many chapters now. So what I want you to do, now that we have our little roadmap here at the top, I want you to try this problem independently. There's no major conversions you have to do. The molar mass of gallium chloride I'll give to you. It's 176.07 grams per mole. Okay, so pause your video and try this problem independently. Our first step is to take that volume of HCl and multiply it by the molarity, because our molar triangle, this gets smaller every time I write it, okay? If we want to solve for moles, we take molarity and multiply it by the volume in liters. We're given the volume in liters, so we don't even need to do a second conversion. So we take 2.6 liters and multiply it by 1.44 molar to get moles of HCl out. So 2.6 times 1.44 gives us 3.744 moles of HCl. Now that we have moles of HCl, we can convert to moles of gallium chloride through a mole to mole ratio. We have a balanced equation, we have moles of HCl, so we are able to convert. So when we react 6 moles of HCl, that's 6 coming from my balanced equation, I get out 2 moles of gallium chloride. Right, that 2 is coming from our balanced equation. So we'll take that 3.7, we'll multiply it by 2/6, and we get out 1.248 moles of gallium chloride. Okay, so now that we've successfully converted from one chemical species to another, we can use our molar mass to go from moles of that species to mass. So 1.248 moles of gallium chloride, I'm going to multiply by the molar mass in order for moles to cancel. And I'm going to be left with, let's see, 1.248 times 176.07. So we get 219.74 grams of gallium chloride. We have 2 sig figs in our problem, so we want to do 2.2 times 10 to the 2 grams of gallium chloride. And that is our final answer. So this was gravimetric analysis, where we take a solution or some initial reactant and we find the mass of the product, assuming that this reaction goes to 100% yield, 100% completion. So we were able to take volumes of solutions and their concentrations and determine the mass of the product that we were going to get out. The other type of chemical analysis that we can use is an acid-base titration. This is a quantitative study of acid-base neutralization reactions, and this is conveniently carried out using a technique known as titration. A titration is a volumetric technique that uses burettes. And it's volumetric because we know exact, oops, I need a pen, not a highlighter. We know exact volumes of the acid and the base. Okay, if we know the exact volumes of the acids and the bases, okay, we typically use this to find the concentrations of the acids. So, if we're using solutions, we have one solution of known concentration and one solution of unknown concentration. If we know the volumes and the concentrations, we can find the unknown concentration. The point in a titration where the acid has been neutralized is called the equivalence point, and this is when the reaction has completed. All of the acid has reacted with the base. And we have no more left. We have no more acid left to react. The equivalence point in a lab setting is usually signaled by a color change of our solution. The color change is brought on by the use of an indicator. Indicators have distinctively different colors in acidic solutions and basic solutions. So here we see a titration going on. Okay, when here base is being added to an acid. Okay, so it's being added in, and there's an indicator in the acid that when it comes in contact with the base, when it becomes basic, it turns pink. So we can see that as we start to add the base in, portions of that solution are turning basic, but if we mix it up, it goes back to clear. At some point, when enough base has been added to neutralize all of the acid, the solution stays pink because it's more basic than it was acidic. Okay, it's more neutralized. So we go from this clear solution to this pink solution, and that tells us that the reaction is done. This is a very strong laboratory technique. So if you're in the lab course for this class, you will be going through some titrations. If you go on to General Chemistry 2, you do a lot more titrations because they are so precise in their measurement and they tell us a lot of information. So even if you're not in the lab, we can use the concept of acid-base titration in order to determine the concentration of an acid. Okay, if you do this in a lab, you're finding the concentration of an acid based off of given data. Here is that given data. So we can use our knowledge of molarity and multimole ratios to help us solve acid-base titration problems. So for this problem, the end point of a titration, so when the titration is done, the reaction is completed, of a 50 milliliter sample of HCl was reached by addition of 45.87 milliliters of a 0.350 molar solution of barium hydroxide. So here's our acid base. Oh, I have this wrong. This should be barium, not calcium. Silly me. So we have an acid-base neutralization here. We have our acid and our base. We know it's a base because it has an OH on there. Our products are a salt and water, and we have the balanced equation there. So if we look at our molar roadmap, if we want to go from one substance to another, we need to go between a multimole ratio. I'm given the volumes, okay, of two solutions and the molarity of another. So I can use my molarity knowledge to go from volume and molarity to moles of one substance. Use our multimole ratio of another or from that balanced reaction, I should say, to get the moles of the other substance. And if I know moles of that substance and its volume, I can find its concentration. Okay, so this is using our molarity triangle a couple of times. So here's my molarity triangle. So the first thing we want to do is find the moles from our concentration and our volume. The only concentration we have is of barium hydroxide. So the first step we're going to do is find the moles. Here I should say we're going to take the liters of barium hydroxide and convert it to moles of barium hydroxide. Okay, so we'll use the molarity to do that, and we'll use our molarity triangle to help us out. Once we have the moles of barium hydroxide, we want to find the concentration of our acid, so we're going to somehow get to moles of HCl. If I'm converting from one chemical species to another, I have to go through a mole-to-mole ratio. There is no other way. So I'll go from moles of barium hydroxide to moles of HCl. That's the heart of our problem, a mole-to-mole ratio. Once I have moles of HCl, I can convert that to molarity of HCl using my volume. Okay, so I'll use my molarity triangle again. If I want to find molarity, I'll do moles over liters. I now know moles. I already have my liters. Therefore, I can solve. So let's start this problem. The first thing we want to do is we want to go from volume of barium hydroxide to moles of barium hydroxide using the molarity. Well, my volume of barium hydroxide is in milliliters, so I'll have to convert that first. So we start with 45.87 milliliters, and we divide by 1,000. So we get a volume out of 0.04587 liters. And that is of barium hydroxide. Our molarity triangle says if I want to find moles, I need to take the molarity and multiply it by the volume. So I'm going to take that volume and multiply it by my molarity, 0.350 molar barium hydroxide. So we'll multiply, and we get out 0.0161, here we'll do 05, moles of barium hydroxide. So we have gone from volume to moles of barium hydroxide. Once I have moles of barium hydroxide, I want to go to moles of HCl, so I'll have to use my balanced reaction. So we'll start with 0.01605 moles of barium hydroxide. And based off of my balanced equation, for every 1 mole of barium hydroxide, I need to react it with 2 moles of hydrochloric acid, HCl. So I'm going to take my mole value and multiply it by 2 to get 0.032109 moles of HCl. Okay, so now I have moles of HCl, and I said we're going to use our molarity triangle to get to concentration of HCl. So if I want to find concentration, I'm going to cover that up. I need to take my moles and divide it by my volume in liters. Well, I have my moles, but I have my volume in milliliters. So we want to convert this. So we're going to take 50 milliliters, divide that by 1,000, and we get out 0.05 liters. Okay, so I have moles of HCl, I have volume of HCl, meaning I can now solve for molarity, which is what we started this lesson with. So now we're bringing it all together. So we want molarity of HCl is going to be equal to 0.032109, that's our moles of HCl, divided by our 50 milliliter or 0.05 liter solution. So we take 0.032109, divide that by 0.05 to get a concentration of 0.642 molar. So that is the concentration of our HCl. Okay, so we started off with our knowledge of concentrations to find the moles of barium hydroxide. So that's our new knowledge of concentrations, how we can use molarity and volume to find moles. We then used our previous knowledge of going from moles of one chemical substance to moles of another through a balanced equation. We used a mole-to-mole ratio to do that. So that was our previous knowledge. We then were able to use our new knowledge of molarity to find the concentration of this acid because we knew the moles, we knew the volume, and we said, well, if I know moles and I know volume, I can find concentration. That's what we just learned about with concentration and molarity. So with a quick conversion into the correct units, we were able to find the concentration of that acid. And this is how titrations work. We use our previous knowledge of molarity, or our new knowledge of molarity, our previous knowledge of mole-to-mole ratios, as well as our knowledge of molarity again. So let's continue to use that knowledge. We want to determine the volume in milliliters now, okay, we need to be specific in milliliters, of a 1.025 molar HCl needed to neutralize the following. So I have 100 milliliters of a 0.30 molar NaOH solution, and I have 100 milliliters of a 0.910 molar BaOH2 solution. So that's what we just did. We did barium hydroxide. The first step to each of these problems is to write out your balanced equation, because if you are converting from one chemical substance to another, you must go through a mole-to-mole ratio. If you do not have a mole-to-mole ratio in your work, you did it wrong. There is no other way to convert from one chemical substance to another without a mole-to-mole ratio. And the only way to get that mole-to-mole ratio is through a balanced chemical equation. So, for this one, we're going to write out our balanced equations. We have HCl reacting with NaOH. This is an acid-base neutralization reaction, so we know we're going to get out H2O and NaCl. Okay? So, this equation is balanced. Everything is in a 1-to-1 ratio, so we can now use that to solve our problem. Our second equation, we already had the balanced equation for, so we had HCl plus BaOH2 creates H2O and BaCl2. I think we had a 2 on the water and a 2 on the HCl. So now that we have our balanced equations here, we have our concentration of acid, we have our concentrations of our bases. We want to know how much of that hydrogen or of that HCl is needed to neutralize these reactions. So think of your knowledge of molarity, our molar triangle, as well as our mole-to-mole ratios to try to find that value. So pause the video and try these two problems independently. So our first steps in each of these is to utilize our concentration and volume of our bases to find the moles of bases. So we know we're going to have to take that concentration and multiply it by the volume. We just need to convert those volumes into liters. 100 milliliters divided by 1,000 is 0.1 liters. So we take 0.1 liters, we multiply that by the concentration, to get the moles of the base. Once we have moles of base, I should probably put some units on there, Once we have moles of base, we can then convert from moles of base to moles of acid using our balanced equation. So for 1 mole of NaOH, I use 1 mole of HCl. In this one, it just gives me 0.030 moles of HCl out. Now we have moles of HCl and we have a concentration of HCl. So we want to find the volume based off of that. So our molarity triangle tells us if we want to find volume, we have to take the moles and divide it by the concentration. So we'll divide that value by 1.025 molar to get our volume in liters. The question asked us to find the volume in milliliters, so we just need to multiply by 1,000. And we get out 29.3 milliliters of HCl. So 29.3 milliliters are needed to neutralize 100 milliliters of 0.30 molar sodium hydroxide. So let's do this again for our second problem that we have. And again, if you feel the need to practice this with me, feel free to pause your video and try this now that we've gone through one. Try the second one on your own and then come back to the video to check your work. The best thing about learning this is that if you get stuck, you can use the videos to get unstuck, and that makes you learn the topic even more. So we're going to start again with our 0.1 liters of now barium hydroxide and multiply by its concentration of 0.910 molar. So we take 0.1, we multiply by 0.910, and we get 0.091 moles of barium hydroxide. Now that we have moles of our base, we can convert to moles of our acid using our mole to mole ratio. So for every 1 mole of barium hydroxide, I need to use 2 moles of HCl. And again, I'm just getting this from our balanced chemical equation. So we'll take that 0.091, we'll multiply it by 2 to get out our moles of acid, 0.182 moles of HCl. Our molar triangle tells us to take the moles and divide it by the molarity to get the volume. So we'll divide by 1.025 molar again to get out a volume of 0.17756 liters. In order to convert it to milliliters, we have to multiply by 1,000. And we get out, oops, I only multiplied by 100. I had another 0 on there. We get out 177.56 liters, which becomes with what, 3 sig figs, 177 milliliters of HCl. So there are our 2 answers for these 2 problems. So again, we're using our new knowledge of molarity and the molarity triangle combining it with our previous knowledge of mole to mole ratios to solve for concentrations and for volumes. Okay, our last two problems are similar, except now we have NaOH and we're reacting it with two new acids. So the first thing you want to do is write out the balanced chemical equations for both of these reactions, because if we're converting from one chemical species to another, we must use a mole to mole ratio. And in order to find the correct mole to mole ratio, we need a balanced chemical reaction. So these are acid-base neutralizations, so we're taking the acid, reacting it with the base, and getting out water and a salt. So we can balance this with a 2. Okay, and then we have H3PO4 reacting with NaOH, and we get out H2O and sodium phosphate. And we balance with some 3s. Okay, so our setup for this is very similar as what we did previously. We're going to want to convert our volumes to liters, use our molarity triangle to get to moles, moles of our acid, convert to moles of base. Once we have moles of base, we can use its concentration to calculate volume. And again, we want our volume for these in milliliters. So these two problems are exactly like the ones we did on our previous slide. So please try these independently. You may see similar ones on your homework and on your exams. So we'll start these off by converting our milliliters to liters. So 25 milliliters, we divide that by 1,000. So 25 divided by 1,000 is equal to 0.025 liters. So we're going to take that volume and we're going to multiply it by our concentration per our molarity triangle. Oops, why did I put a 2? That will give us our moles of our acid. So that's 0.1125 moles of H2SO4. Once we have moles of H2SO4, we can convert it to moles of our base, which is NaOH, using our balanced chemical equation. So for every 1 mole of H2SO4 I need to also use 2 moles of NaOH. And from that, we can find our moles of NaOH. So we multiply it by 2. So that gives us 0.225 moles of NaOH. If we have moles and molarity, we can divide those two values to find volume. So we will divide by the concentration of NaOH, which is 1.015. And we get out 0.22167 liters. To convert to milliliters, we multiply by 1,000, and we get out 221.7 milliliters. 4 sig figs coming from our problem. We'll do the same thing for our very last problem of this lesson, where we'll start off with our volume, 0.025 liters, multiply it by the concentration, and we get out 0.0375 moles of H3PO4. We'll then use our mole-to-mole ratio to go from moles of acid to moles of base. So for every mole of acid I use, I need to also use 3 moles of NaOH to complete the reaction. So we'll take that and multiply it by 3. Once we have our moles of NaOH, we can use its concentration to find the volume. So 1.015 molar. So we'll divide by that. That's from our molar triangle or molarity triangle. And that gives us a volume of 0.110837 liters. We'll multiply by 1,000 to get milliliters. And that's 110.8 milliliters for significant figures based off of our problem. Okay, the biggest thing that I want to point out with titration problems, and I'm going to write this in big letters and in red. Never use M1V1 equals M2V2 for a titration. Never ever. If I see it, it's marked wrong. Okay? Never use M1V1 equals M2V2 for a titration, because M1V1 equals M2V2, that's a dilution. A dilution is not changing any of our substances. A titration, we are converting between substances, and the only way to convert between substances is to use a mole-to-mole ratio. So titrations must use a mole-to-mole ratio. Nowhere in M1V1 equals M2V2 is there a spot for a mole-to-mole ratio. Nowhere in there is there that value. So we can never use the dilution equation to solve a titration, because those are two different concepts. So if you are ever using M1V1 equals M2V2 for titration problems, you are wrong. You will always be wrong, because you are not accounting for a mole-to-mole ratio to go between your acid and your base. So please keep that in mind. Always use your steps using our concentrations to go to moles. Once you have moles, use your mole-to-mole ratio, and then use your molar triangle again. Okay? You must use a mole-to-mole ratio in a titration problem. If you are ever changing your chemical species, you have to go through a mole-to-mole ratio. There is no ifs, ands, or buts about it. The only value that allows you to convert from one chemical species to another is a mole-to-mole ratio. You must use it. So, go to your ALEKS homework and practice these types of problems, typing them into your calculator, making sure you understand how to use them in your calculator, writing out all of the steps, using those new triangles and those new equations and these new units. Practice, practice, practice.